So we were talking that the light is electromagnetic wave. What does it mean, electromagnetic wave? When we were observing the wave on the screen, it was obvious the particles of the screen oscillates up and down, or on an or forward backwards when we looked into the longitudinal wave. It's clear what's oscillating in like water waves, but what is oscillating in electromagnetic wave? Electric and magnetic fields. What does it mean they oscillate? That means at certain point of space, we have that at this point of space, let's say electric field at the moment is 0. Then it becomes like this. Next instance it becomes like this, then becomes like this. And then it starts decreasing, becomes like this, becomes again 0, start increasing in the opposite direction, more, then again back decreasing to 0, and again. That what means the strength of electric field at that point oscillates. It changes direction, becomes maximum in one direction, back to 0, maximum to the opposite direction, back to 0, and again. That's what does it mean, oscillates. And so does magnetic field at the same point. And those oscillations are transmitted through the space. And first of all, let's look on the picture how it all looks like. So, this represents the electromagnetic wave, represent the light. So light travels this direction. Red represents the oscillations of the electric field, and the blue showing the oscillation of the magnetic field. As you can see, they oscillate at the 90 degrees to each other and 90 degrees to the direction of the wave propagation. How you can find, for example, if you know the direction of magnetic field, how you can find direction of the electric at that point? We can use, because it's all three-dimensional problems, what we were using when we were facing three-dimensional problems with the magnetic forces. Right-hand rule. We'll use right-hand slap rule as well. If you place right hand, that fingers will show direction of the magnetic field. So in this case, out of the board. This finger will be in the opposite direction, light travel this way. We put finger in the opposite way, and electric field coming out of our palm, going up. So magnetic field, out of the board. This is the opposite to the direction of the light. Light travel this way, so finger that way. Then electric field will be coming out of the palm, will be up. In the same way, if you look here, we have magnetic field into the board, light direction opposite to the light propagation, electric field down. So that's how we can find direction of the electric field. With the magnetic field, if you know direction of electric field, then you place your fingers direction of the electric field. This is direction of the light, not opposite, and magnetic field coming out of your palm.
Couldn't you also just do, like, just take palm as always electric field, and fingers always as magnetic? Couldn't you always take palm as?
No, I mean if you have, for example, given to you direction of magnetic field, you need to find direction of the electric field. Or opposite, you have given direction of electric field, need to find direction of the magnetic field. So just remember, from magnetic to electric, finger opposite the direction of the light. From electric to magnetic, in the same direction. Just make a note.
Can't you just use, like, if you don't know the magnetic field, and you just put your hand like that, and that's your electric field, that's your...
Yeah, you can do that in reverse. First, like option in reverse. Yes, that it's from the palm coming. You know that from the palm that gives you direction.
So the direction of the light is the other way.
If you're the second option, direction of light is the same.
Yeah, it's electromagnetic.
Yes.
How can we take the current in the opposite direction?
Not current. There's no current. It's direction of the light propagation.
Yeah, but then
And this is not like something happening in physics. It's just to help you identify the direction.
But why would we put our thumb in the opposite direction that the light's traveling?
Because you have not learned cross product of vectors, which couple people in the class do in the specialist unit 3-4. So we need to use.
That's next week.
If you don't know some mathematics, then you need to use those things. If you know cross product of vectors, you pretty much will be. But then will be this right hand rule can be helpful with the solving problems with the cross product of vectors. Now, we already know that what's induced current. What should happen for current in the coil to be induced? We need magnetic field changes. And current if you have current, that means there is an electric field which acts on the charges. So change in the magnetic field creates electric field. And so change in the electric field, if you have current, what's create magnetic field? Moving charges. So change in magnetic field creates electric. Change in electric creates magnetic. And English physicist Maxwell, he sort of believes that electric and magnetic phenomena is like two sides of one coin. And he, based on known information, he derived 4 equations which describe all electromagnetic phenomena. Everything, all laws related to electromagnetic field are in there. No, you can see even who doing specialist math, they never seen anything like this, even this notation. They don't know what does it mean in a control integral. And or even there are 2 forms of those equations. That's integral form, and there is a differential form. Again, even notation doesn't tell. Even people doing specialist math does not take much this sign. Divergence of vector, never use that. So the mathematics of those equations is like beyond school curriculum. But what's important? That he derived those equations which describe, including Faraday's law, everything coming out of those equations. And there is important constant that he found in his equation, C. You see, we have C squared, C squared, C squared. And he found that was a speed of electromagnetic wave. And it happens that speed of the electromagnetic wave derived by Maxwell is exactly the same as the speed of light. So that that's where we can make conclusion. Another like thing supporting that the light is electromagnetic wave. Now going back to previous picture. So what's important for light, for electromagnetic wave to be created, there is needed a change. And so change in electric field creates change in magnetic. So such change in, let's say, electric field, it will create change in magnetic, which in turn create change in electric, which in turn create change in magnetic, and so on. And that's how light is propagated. When change one field changes, create change in another, in its turn it create change in the first, and so on, and light moving. And so light doesn't need any medium to travel, it can travel through the empty space, because electric and magnetic field can oscillate in the empty space. Another thing, to create electromagnetic wave, if you will have just moving charge. We have charge and we move it with a constant speed. We will not create electromagnetic wave. We create magnetic field, but there will be no change. So, to create electromagnetic wave, we need to accelerate charges. Any accelerated charge creates electromagnetic wave. So when charge accelerates, it creates electromagnetic wave. And this acceleration can be accelerate, let's say, electron from minus to plus, or moving in a circle, because remember, motion in a circle is motion with acceleration, so change direction, change its velocity, that will be creating electromagnetic wave. Now, I'm jumping a little bit into the next area of study, where we'll look into this in more detail, but what in the atom, we were talking till now about the electrons moving in the orbit like planets of the solar system. This is like sort of approximation for younger kids to better understand the structure of the atom. But you know that if charge moving with acceleration, and motion in a circle moving with a constant speed is motion with acceleration, what should be happening? Electromagnetic wave should be emitted. And so electrons should be losing energy, rotating, because when you emit energy, you lose energy. And eventually it should fall on the nucleus. It should not happen. So this is a too simplistic model. Later on we'll learn more about the real model, but in fact it's wrong. Electrons does not orbit atom in an orbit like planets orbit the sun in the solar system. We can say only about the areas, and they actually behave as waves. And we can talk only about probabilities of electrons being there. And when it's in this stable orbit, sort of, but which is not correct because there is no orbits as steady orbits, it does not emit any electromagnetic waves, even moving with acceleration. Only when it's jumped between between the orbitals, it's emit or absorb energy. Again, that all in next area of study, much more in detail. Just to understand now that accelerated charges emit electromagnetic wave. And the electron in the atom does not behave like a planet in the solar system. It's all much more complicated. Everything when we get into the micro-world is very different to our everyday experiences, and we'll learn more about it a little bit later on. Now, when electromagnetic light is created, we have electromagnetic wave. The oscillation of the electric field, for example, not necessarily happens all the time, like in this direction. They actually rotate. It rotates this instant, it oscillates this, then it can oscillate like this, and so magnetic field will turn again and again and again. So it does not have steady plane of oscillation, it changes. But there are some certain materials which allow oscillations of the electric field only in one direction. Let's say we have this material which allow, so before we have electric field oscillates in all directions. This instant this way, and another instant this way. And then we have material which allow oscillations of the electric field only in one direction, due to the structure of the material, the interaction of the light with its atoms. And what will happen when light gets through this, it becomes polarized. What does it mean, polarized light? Is a light that have oscillations of electric and so magnetic field only in one fixed plane.
Sorry, could you repeat that?
What polarizing field does, it's when light comes through the polarizing filter, through the material, which allows oscillations of electric field only in one direction, the light coming out will be polarized. Its electric field will be oscillate just in one direction, and so magnetic field perpendicular to it. And if we will put another filter from same material, but we'll turn it 90 degrees. So if this one allow oscillations in vertical direction come through, this allow only horizontal. What will come through? Nothing. I will do this experiment a little bit later on, when you will observe, when you just turn it to filters and you see suddenly they were transparent, suddenly they become non-transparent, because of the polarization. So that is a little bit about the light as electromagnetic wave and polarization of the light, which is one of the important things that confirms that the light is transverse wave, that it can be polarized. The longitudinal wave cannot be polarized. Cannot be polarized. Now we're going a little bit back to mechanical waves, then we'll come back to light again. But if we have, going back to mechanical waves, first, if we have wave traveling to the right, and at certain instance of time, we see the wave looks like this. At certain instance of time, we take a photo of the wave. It looks like this. Let's consider a few points on this point A, point B, point C, point D, point E, point F. Question is, and the wave is the transverse wave, it's traveled to the right, oscillations happen up and down. Oscillations happens up and down. Question is, in which direction, at that instance of time, each point is moving?
Down.
Now, they will be moving in different directions. How we can find it? Yes?
Is it maybe if it's a negative gradient and moving down, if it's a positive gradient and moving up?
The best way is to sketch this, how this wave looks like next instance of time. If waves travel to the right, so we have the wave will look like this. That will be next instance of time. Wave move to the right. Now let's see where each point moved. Where point F moved? Moved down. It was here, now it's F is here. So F moving down. E point, remember, point though, matter not going with the wave. Wave with the transfer of energy without transfer of matter. So those points that oscillate up and down, they're not moving with the wave. So that's how wave looks. So this point will be here. Where point E going? Down. Where point D going?
Up.
Now, this is a little bit tricky. At that instance, it's stationary because it needs to change direction. It is stationary, about to move up. Point C.
Up.
It's moving up.
B is up.
B is up. A, stationary, about to move down. Does this logic make sense, understanding where each point is moving? You need to sketch how the wave looks next instance of time, and just look vertically, because points moving vertically. They're not moving with the wave, move up and down. You just need to look where this point will be next instance of time. You can identify in which direction it's moving. Make sense? Okay. Now, if we have wave looks at some instance of time, wave looks like this. How these waves, it's travel this direction, and again points oscillates up and down. 1/2 of the period later on, how this wave will look like. In the half of the period. Remember what the period? Time of one complete, when time required to make one wave, or time of one complete oscillation. Yes?
It's going to be like doubled. It's like it's going to be like 2 in like the 1. I don't know how to explain.
No,
How it
periods
will
and
look?
half,
Yes,
half
it will.
like flipped.
It will be like reflection in x-axis. That will be half a period, because in the half of one period, this point moves to the bottom and returns up. That will be one complete period. So half of the period, it will get there. How it will look like quarter of the period later. How it will look quarter of the period later. So that was half of the period, quarter of the period later. How it will look like.
Cosine graph? A cosine graph? It's a cosine graph. It's a cosine graph. It's a cosine graph. It's straight line.
Straight line. It will be a straight line.
What is it straight?
Because if this is a half of the period from this point get to here, in a quarter of the period where it will be just here. This point will get here, in quarter of the period you will see just like that. It will be straight line. That will be quarter of the period later on. Does that make sense?
Yes.
Now, we were talking before about the superposition of the waves, how waves adds up when they meet. Let's consider if we will make a wave on the string. And we will have this wave reflect from the opposite end. And we will let this wave to reflect from the opposite end. And then we will have two waves traveling towards each other. So, I will create the wave. Now, we look fixed end. It will be a little bit different with if end is not fixed. So let's start. So we start making at one end wave is fixed. String is string is fixed, and we start to move it the string up and down on the other end. And we have wave travel through the string, and it will get to the fixed end and will reflect from it. Now, how it will reflect? It will reflect at that point, when this point will reach here, will it reflect exactly as it's coming, or it will flip?
Flip.
Yes, flip. Why? Why it will flip? this point is fixed. So when wave comes, it will start to pull this point up. Third Newton's law. Then this pole will pull wave down, will apply force on the wave down. That's why reflected when from the fixed end, wave will flip due to the third Newton's law. So you see, wave reflected, it's flipped. And now we have two waves travel along the same string in the opposite direction. One track continue because we continue to make wave on the left end. So one wave travel to the right, another wave travel to the left. And where they meet, they add up. We have a superposition of the wave. In fact, we will not see all those waves, one wave coming and one reflected. So what we will see only this. In fact, there are two waves. One moving from left to right, another moving from right to left, reflected wave. As a result of this superposition of the waves, we will get this, what we will see, only one wave. But in fact, there are two waves there, adding up, and all the time they superimpose on each other. But we see only the result of that superposition. And this wave called standing wave. This type of wave, this is, and on exams they like to test understanding of the standing waves. It's highly likely to have a question explain why it's standing, how standing wave is formed. Why it's called standing wave? Why do you think this type of wave called standing wave?
Standing?
Because we see some points never moved. They always stationary. And some points always oscillate at its maximum. So positions where we have maximum, A, not changing. Position where it's no oscillation at all, not changing. That's why it's called standing waves. So conditions to create standing wave. Make a note. Conditions to create standing wave. And it's not only on the string in general. Standing wave created when we have traveling wave and reflected wave. It's important to say reflected wave, traveling wave and reflected wave superimpose on each other. So it's important, two waves, one traveling, one reflected wave, superimpose on each other, creating nodes and antinodes. Nodes and antinodes. Nodes and antinodes. Node is the point where they cancel each other. They superimpose on each other, creating nodes and antinodes.
So there's no...
Node is the point where they cancel each other, where destructive interference happens. They cancel each other at those points where and node. Again, I'm showing you two waves, and I will pause so you will be able to see. So where the node, they always meet each other in the opposite direction. That's why we will have here, where is a node, we will have destructive interference. They always cancel each other. And at the antinode, it's all changing. They meet in phase. And we have constructive interference. And we have a bigger amplitude at that point. So they superimpose on each other, creating nodes and antinodes. Now, how we can do calculations with let's consider the string fixed at both ends, and we have length of the string is L. What will be the longest standing wave that can form here? What will be the wavelength of the longest, how it will look like the longest possible wave? Longest possible wave will look like this. We here always will have node. But those points cannot move, they fix. So it's always node here, node here. So we can have node and we have one empty node where it oscillates at its maximum. So what is the relationship between the wavelength and the length of the string? What we can say, what the relation between the wavelength and length of the string? Wavelength is double the length of the string because this is a half of the wavelength. Make sense? What will be the next possible standing wave created in this string? Then will be next possible when we have, it's like this. Because at the ends we must have nodes. So we'll add another node. So we have, before we have two nodes, one empty node. Now we have three nodes and two empty nodes, because this will be two empty nodes. Two empty nodes. So what will be the relationship between wavelength and the length of the string now? They are equal. This is the wavelength and this is the length of the string. So we have equal 2L over 2, which is equal L. Next one, if we continue this pattern, we'll have 4 nodes, 3 empty nodes. If we continue this pattern, the next will looks like this. Again, remember we must have nodes at the end. So that the next possible, which must have now, we have 4 nodes, node, 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 and we have 3 empty nodes. What the relationship between them now? Wavelengths equal? 2L and 3. Can you see the pattern? What will be the next possible wavelength? 12 and 5, and so on. So,
wait, why is it 12 and 5 and not 12 and 4, the next one?
Sorry, 12 and 3, 12 and 4, 12 and 5, yeah. And so on. We have only in the course, they left only fixed, standing wave fixed at both ends. So we're not looking if one end is free. That will be different mathematical relationship, but it's not part of the course. So it's quite a lot of my explaining for today. Like, subscribe, and donate to help fight evil countries and organizations like Russia and Hamas. Support Ukraine and Israel.